Hi, everyone. So today I'm here to talk about some MLIR internals, namely OpInterfaces. So it's this kind of talk where you're not going to hear about dialects or operations or attributes or type, which is a bit unusual for an MLIR talk, but let's dive in. So the agenda for today is some implementation background on how we came up with OpInterfaces. So you're going to see a lot of code on the slides. And then I have some more details on the current implementation, what we have. And so there's going to be a lot of code. Just brace yourself. I hope you had enough coffee to follow. I'm going to just explain a bit what the ODS generation map to. By this time, you should have a good intuition about how the pieces fits together. And then if we have time, we're going to try to cover the external interfaces and the promises mechanism that comes with it. All right, so why interfaces first? What's the motivation behind it? So this is LLVM code. There is a function I just copy-pasted from the code base, get arithmetic instruction cost. The way it's implemented is like most LLVM function, it's going to switch on the opcode, and it takes advantage that LLVM has a closed set of instruction to try to pull properties about those operations. Right? But MLIR doesn't have a predefined list of operation, and we still want to write generic analysis and transformations. So what we do in MLIR is that the body of this method would instead look like this. It would be a dincast to an interface that would be instruction cost OpInterface, for example. The interface is defined by the analysis or the transformation in general. It exposes the kind of properties that the analysis wants to know about the operation, and the operation implements the interface to provide the answer. So it's a query answer mechanism. And this is how MLIR decoupled the implementation of analysis and transformation from the operations. So many people always are confused or ask me about traits versus OpInterfaces, and wanted just to clarify this here. What are traits? Traits provide the ability, two things. First, the ability, a Boolean ability to check if an operation implements a trait. So this is the op has trait method. And this just allows to check a property. Does this op has this property? Is this op pure? Does it have side effect? You can query this and get a Boolean answer. It also provides a base class for the concrete operation, but without virtual method. So it's only adding behavior and method as a refactoring thing. It's like all the op in my dialects will have this implementation, for example. The interface on top of a trait, because the interface also provides traits, it adds polymorphism. It acts as if you had virtual method on the concrete operation. So it's a base class with virtual method, conceptually, and we're going to see how it's implemented. So a trait, an example of trait would be a linalg trait. All the linalg operation will inherit this trait. And that means when you have a concrete linalg operation, you can call this method getNum parallel loop, which is implemented in terms of other properties of the operation, right? And the implementation doesn't matter here. It's just for the example of what the trait is and to really explain that there is no polymorphism involved. When you have an opaque operation pointer, the traits doesn't really help you here. So that's the trait behavior. You need to cast to the concrete type to be able to use it. OpInterface, on the other hand, provides a similar mechanism to what would be a virtual base class. And that's where we started with OpInterfaces. Nicholas was trying to get this polymorphism for linalg operation more than 5 years ago now, and came to me with this code trying to add virtual base class to the concrete operation, right? And the problem is that then when you want to have polymorphism, you start from an opaque operation pointer. And polymorphism in C++ requires you to have an instance of the derived class. And here we don't have an instance of the concrete op. What we have is the opaque operation pointer that we're trying to cast to the interface, right? So that cannot work. There's never an actual instance of the derived class to get the virtual table here. So what we tried to do and what Nicholas was playing with at the time was this kind of code where we would type switch on the operation pointer. And so we would do basically a dincast on all possible linalg operation and try to cast them to the concrete implementation and then build the interface from that, right? So now we have a concrete instance of the derived class and we should be able to get the base class, right? There is still a problem here is that we return the base class by value And in C++, when you do that, you lose, you no longer have an instance of the derived class, so you have now the virtual method of the base class. If you were calling any of the virtual method, they would resolve to whatever implementation is in the base class. So this is the slicing problem of C++. So to solve this, what you have to do is to use either pointers or reference. And so the type switch would look like this. And the problem is that now for every cast, technically, to an interface, you would have to heap alloc and copy to be able to do that, which would be pretty inefficient. Another problem with like what we're doing, it would work for linalg because it's a closed set again, but it's not very extensible. Now we are back to a predefined list. It's really not what we want. So one of the fundamentals in MLIR, and that comes from the slicing problem, is the concrete operation cannot have any state, right? And now we added since then a static assert because many people fell into this trap of trying to add members to the concrete op. The only state is inherited for those concrete op. It's a single pointer to the opaque operation. All the behavior that the concrete op adds is through access to this pointer. All right, so how did we solve this at the time? At the time, I was pretty inspired by this talk from Sean Perrance at Going Native 2013, which was named Inheritance is the Root of All Evil. In this talk, he showed how to do polymorphism in C++ without inheritance. And it's a bit hard to piece the pieces together, but I'm still going to try to explain it. So now the interface doesn't have any virtual method. We cannot have virtual method, and that's pretty good for us because we don't want any state. Even the virtual method pointer, the virtual table pointer is kind of state and would be sliced. So instead, we dispatch to a self member, and here is the following content of the class. The self pointer is a pointer to what Sean called a concept class, and this concept is the actual virtual API of the interface. And we have a model, and the model is the concrete implementation, the derived class. And here the model just has also an implementation and will dispatch. So we see that there's many layers of dispatching. It's a bit hard to follow, but this is where the terminology comes from in MLIR. Right now, if you hear about concept and model, this is coming from this talk. And so I invite you to all watch this talk or the slides and try to get those pieces together. And the last piece to make everything work together is the constructor of the interface. When you construct the interface with an object, this object doesn't have any inheritance relationship here. We copy it into the model. And so the model on the right side here will take a copy of the concrete op. It stores it as a member, and it will dispatch to the concrete op through its own virtual method. So as often in computer science, everything is solved with one more level of indirection and a lot of templates. So the only constraint here is that it's kind of duck typing. It's that the method must exist on the concrete op, and then everything here is just going to plumb this virtual dispatch mechanism at the cost of multiple layers of indirection. Another problem is that we still cannot construct this generically from an operation. Like the constructor wants the concrete operation here. So we are not there yet with this. But we made some progress in terms of not needing any inheritance. Also, like the implementation that Sean proposed was still heap allocating, which doesn't really fit what we want to do. It's far too heavy. So we're going to look a bit about like the pieces here. We have a shared pointer to the concept, the base class, and the actual implementation, the instance, is also keeping a copy of the concrete op. What we want instead, we want it to be stateless, to be able to not allocate every time. What we're going to do is that now the model is fully stateless, and instead we changed our interface. So the method, the getParallelLoop method, now takes a pointer to the operation, at least in the concept and the model, which are not visible to the users. Those are private implementation of the interface. So we pass the state explicitly, and that makes it so that our model is stateless. And if the model is stateless, it can be common for all the operations. And so we can pre-initialize it in the MLIR context ahead of time, and we don't need heap allocation on every cast anymore. All right. Now, what we still need to do is solve the creation problem. So when we initialize the interface. We want to initialize the interface on the left side here from an opaque operation. And so the way we do it is that now we have this model that is stateless, can be allocated once when we initialize the context and register the operation. And so we're going to store it in the context in what we call the registered operation name, which is attached to every operation. And this registered operation name will have a map of type ID of an interface to the model implementation. So for any interface, we can query the operation name in the context and get back this instance of a model, which is really this virtual table. What we really want at the end is this virtual table. And that's how we can now initialize interface opaquely. And this is what happened every time we do a DIN cast. So when we do a DIN cast to an interface or cast, there is a map lookup into this registered operation name in the context. Right, and so conceptually now what we have in the interface as state is a pointer to a vtable. And we could save some indirection, and we're going to see how we're going to do it. So just a note on the registered operation name, it's really the source of all the magic in MLIR. This is what, when you register an op, this contains all the metadata, the canonicalization pattern folding, everything is attached to this registered operation name. And so it's pretty powerful as an extensibility mechanism. We leverage this all the time. So what is a vtable and what does C++ does? It's really just a structure defining function pointer. So we can save an indirection here. We rely on the C++ compiler to do a lot of boilerplate for us by generating the vtable and the initialization. But we could go from this like virtual inheritance mechanism to a manually rolled out table of function pointers, right? And so instead of a virtual method, we just store a function pointer. So we inline the vtable in the class to some extent. So the concept class takes the role of the vtable instead of being a virtual base class, right? We still inherit from it here, but what we do, the implementation, instead of overriding virtual method, they become static. It's also possible to do that because we are in a stateless class. Because the state is explicit, we can be static here, and we initialize in the constructor, we initialize the concept, the table of function pointers with those static method. Right? And so now we save one load when we call a method on an interface and do this dynamic dispatch. This is what we do. We could even go further. Instead of having a pointer to the concept, we could take it by value. We could inline the vtable even inside the interface if we wanted to. So that would be a trade-off of size of the interface, which is passed by value often, and the indirection there is when you do a virtual call. All right. So that's the implementation of the cast and DIN cast. So every time you construct an interface, we have this get interface for that is called on an opaque operation pointer. It goes into the registered operation name on the context, but there's one more thing I wanted to point out, is that the dialect can also provide a fallback, right? Because the interface is just a table of function pointer, technically you can provide this implementation in many ways. And so a dialect itself can act as a fallback and provide some sort of an implementation for those function pointers that is a catch-all for all the operation in dialect or for some specific operation, and so there's mechanism here. All right, ODS generation now. Hopefully by now you have some sort of understanding of those table of function pointers, and that's going to make it easier to understand what's happening here. So there are two kinds of interface methods that we have. We have the interface method and static interface method when we define an interface in ODS. It's TableGen code, right? So what is generated? What is generated is the concept, so the definition of those function pointers. And we see that it matches the two methods. And also the model, which is what's the concrete implementation that is templated on the concrete op. Every concrete op, when you register it in the context, instantiates this model class when you attach the interface, of course. And the model is just those static functions that dispatch to the concrete op. So the static variant, the static interface method, is still a virtual dispatch, right? Why do we call it a static interface method? It's a static interface method because it does not take the state, it doesn't take the operation pointers, and it's going to call a static method on the concrete op, right? And so it's limited in terms of what you can do. So you can see the difference between the two operations here in terms of Like the first one is calling a method directly on the concrete op after casting the operation pointer. The second one is calling a static method, right? But both of them are doing virtual dispatch to the concrete implementation. So there are two more things on those interface method and static interface method. There is first one argument, which is method body, which is pretty obscure and hard to use. Actually, there is only a single usage for this in the entire code base. So, it doesn't really pull its weight. What it does, it changes the implementation of the model, right? So you could change the way you dispatch to the concrete implementation. It's pretty rare that you have to do that. The only example that the doc gives for interface is that you would do that if you have a method on the interface that you want to implement in terms of a combination of properties of the operation. And so the mental model you can have here is that it's like defining a non-virtual method on the interface, right? And actually, all of those method body implementation could be implemented differently by using the extra C++ declaration, extra CPP declaration that you can put, like raw C++ you can add to the interface there. Another part of the interface is that a trait is automatically added to every concrete operation that defines that wants to use the interface. And so the last arguments of those interface methods is what we call default implementation. And the default implementation will go into this trait. So this trait is inherited by every concrete op, and this is actually what is called by the virtual dispatch. So when we instantiate the model, it will actually call those methods on the concrete op, whereas where are these methods coming from? They are coming from the traits inherited by this concrete op, right? And so in the interface method in ODS, when you add something for the default implementation, this is where the code goes. It goes in the traits, which is then inherited by the concrete op. And you can always override it when you declare your op in ODS. If you do declare OpInterface method, you can say, I want to override this particular method, and you're going to have, on your concrete op, the ability to override this behavior. So in terms of mental model, if you go back to C++, I have an abstract base class and I override method. It's like if your base class virtual method have a default implementation. You can always override it in your derived class, right? And that's why we call it default implementation here. All right, the last piece to talk about is external interfaces model. Right? Most of the time, you're going to declare in ODS that an OpInterface is attached to your operation. The problem is that when you do that, there is some sort of bloating effect. When I depend on a dialect, I get all the interfaces and all of their dependencies, and that can be pretty big. And the solution was to say we want to decouple adding an interface to an operation. So for example, for bufferization, we have this method, registered bufferizable OpInterface external models, right? And so now if you see models in the name, you can connect back to those concepts from Shan. The model is really this concrete table of function pointers that implements the interface. And so the user has to call this function to attach the interface, this vtable implementation to the operation. If you just load the dialect, the SCF dialect, and you try to use the interface, those operations don't have the interface. Right. The advantage of doing that is that now we can use the SCF dialect without any dependency on the implementation of those interfaces. We don't have dependencies transitively to the bufferization dialect and to all what comes with the implementation of those interfaces, maybe memref or whatever. I want to use just SCF. I don't need bufferization. And this is decoupled. Right. One of the problems is that this is a bit fragile. It's kind of a foot gun, because what happens if you try to use SCF, try to bufferize, but you didn't know you had to also separately load those interfaces and attach them to the interface, right? You're going to spend long hours of debugging. And another example sometimes is that you may not even know that something changed in MLIR upstream and that you would need to do that. You may be just using TOSA dialect, build a pipeline that is compiled TOSA to LLVM, run the pipeline, and now if you need bufferization in the middle, but you yourself didn't know you had to register those kind of thing, it's just going to maybe walk, but maybe slow. And so we're back to long hours of debugging. So the solution to this foot gun is what we call promises. when we initialize the dialect, we declare a promise. We promise that those operations will implement this bufferization interface, but we don't provide the implementation to keep the decoupling. So what we do is poison this map in the context that contains the table pointer, this structure of function pointers. We poison the map, and so when someone tries to cast an operation from the SCF dialect to this bufferizable OpInterface, if the interface hasn't been separately loaded in the meantime, we hit this poison value and we get this nice, or not nice, crash at runtime, which tells you there was a promise that this interface will be there for this operation, but I don't find it. I just have this poison value. And LLVM will crash and will tell you you have to call this registration, right? And so what's missing is just calling this. All right, and so here are some takeaways, and I'm not gonna go through them one by one, but this is what we covered today, and also what we didn't cover, which is in interface inheritance. Attribute types can also have interfaces. It's the same mechanism. A dialect can have interfaces. It's slightly different, but not that much, same concept. And I didn't got into the details of some resolution of dialect fallback, but hopefully you got the gist of it. Thank you.
Thank you, Mehdi. Questions? So we have microphones on the aisle, and I can also pass along this one.
Hi, Mehdi. Very interesting talk. I was just wondering, how much of this work would have been made easier if you use like C++20 and concepts, etc.? Like, would that have helped you in your implementation, or?
So that's a good question. Concepts are really this mechanism for template instantiation, right? About these contracts. I don't think concept would help a lot here because what we're really doing is playing with virtual tables and the virtual dispatch, and less about the templates overloading or contracts that are made available by concept, I think.
Yeah. Thank you.
Hi. Hi. Okay, good. Thanks for the talk again. Newbie question. Have you considered the attach interface feature when you want an external model as something you could bring into the TableGen as well, anyhow? Because problems that I face often is you have an operation defined in TableGen. Half of the interfaces for that are in the TableGen as well, which is easy to track. But then there is always some feature which is somewhere there in a register function, somewhere in the C++. And half of the time I'm like, does it really have this interface, or does it not? And you have to search a bunch of source code to figure it out.
Yeah, the usability and the discoverability of all those pieces, how they fit together and how to get set up is not great. It's not a great user experience. Many people are confused by this, super nice error that we put here. What do I do when I get this error if I don't know about all this external promise mechanism, etc.? There's no good way. I think we need to do better. I don't have great ideas right now, but yeah, if anyone has, we should do better.
So something for an RFC, I guess.
Yeah, absolutely.
Thank you.
Sorry. I wanted to have a follow-up question on the C++20 question. Have you considered const expr virtual in trying to manipulate the virtual table that's available in C++20?
No. So first, because this was done 5 years ago. So I don't know if I was not really looking at C++20 yet. Also, LLVM is still on C++17, so and back then it was C++14. But thank you for putting this on the map. We need to look into that, right?
You likely wouldn't get that nice error.
Yeah.
With const expr.
I mean, this error is really when we look up the map. So when we do a cast, we implement the look up the map in the context. We would still, it's an assertion that we have in our lookup process that would still be there. The const expr virtual, I think, would happen in terms of how the model is set up. I'm not sure. So something we do with those virtual tables that we hand roll is that we can inline them. So we save one indirection by doing so. I don't know if context per virtual would allow us to do so. Yeah, yeah. I need to look into that. Thank you.
Right. So in exactly this thing, we already have the auto registration of dialects for the passes when you don't register them beforehand. If your poison value, instead of erroring, could dispatch into a registration of the interface on that specific thing, then you wouldn't get the error. You just get some slower, late registration, lazy registration.
Yes, the problem is that if the user doesn't know about calling this register thing, the interface is not even in the binary. It's not even linked in.
Oh, I see.
Right? So the problem is that we want the user to be explicit because we don't want to, by default, ship all of MLIR into
you don't
everyone.
want to link all the libraries everywhere. Okay, makes sense.
We're already out of time, so should we have last question?
Okay, just quickly then. Do you know, have you done any measurements for how much this kind of dispatch ends up costing compared to a switch?
Oh, you mean like the LLVM switch?
Yeah.
Yes, actually I have a talk tomorrow morning about efficiency of the compiler, and we try to benchmark like just something like that, right? So come back tomorrow.
Okay, let's thank you, Mehdi, again for the talk.